But I'll give you motivation. One reason that we handed out this homework assignment is that the next homework assignment, which will come out in a few days, builds on this one. You're going to train a deep network for doing character recognition. You're going to train a Linnet. You're going to help implement it. And so understanding down at this level of detail what those gradients really are, what the derivatives really are, how the algorithm really works, is a very valuable step along the way. So hopefully this will be an interesting homework assignment. We've been pre-testing the next one with our teaching assistants who unanimously agree it's a wonderful homework assignment. So we'll wait to get your vote too. Okay, so today I want to continue along the lines of discussing deep networks and looking at some topics we haven't yet. One topic we actually did look at in several algorithms that we've studied is the topic of overfitting. The topic is really not very different in the case of deep networks, except that some of these networks have a lot of parameters, and so it's quite easy for them to overfit. It's not unusual for example, networks for image processing or speech processing to have over 1 million trainable parameters. And so people tend to train those on very large data sets, but nevertheless, overfitting is an issue. And so here are two plots for two different networks that I trained sometime in the past. The dark line is the training set error as a function of the number of weight updates, the number of gradient descent steps that were taken. So you think this is the loss function, the training set error. And then here in a different color is the error measured on a separate set of data that was withheld, which we call the validation set. We're using that not to train the network, but simply to track, to validate how well it will do in the future. And so what you see in both plots is that, of course, the training error goes down more rapidly than the validation set. That's, of course, to be expected because the gradient descent algorithm is, of course, minimizing the loss function on this training data. And in the top plot, for example, you see that the longer you run the gradient descent, unless you have some kind of stability problem or a learning rate misconfigured, the loss should just keep decreasing. That's why we call it gradient descent. But on the separate withheld validation set, you can see that the error originally decreases, but then at some point it starts increasing again. And so when you're done training the network, if you want to use it on future data, then which version of this network do you want? Well, obviously you want the version of the network that's going to do best on future data. And so the least biased estimate of that comes from the validation error. And that's minimum around here. So it's basically this version of the network that you hit after 9,500 iterations of training, that performs the best on the validation set. And so when I train networks, what I usually do is just write out to disk all the weights of the network every 10 iterations or so, depending on how much disk space I have free. And then I keep a validation set of data separate from the training set. And as I'm training, every once in a while, like maybe every 100 iterations, I check how well we're doing on the validation set, or I have the program check how well it's doing on the validation set, so that effectively I have my program plot these two curves during training. And actually the smart way to do it is save the network whenever you have a network that performs better on the validation set than you've seen previously. Okay, so then when I'm all done, I go back to disk, and there is the net set of network weights from this point, because we wrote out the network parameters at that point during training, and then we never overwrote it because the validation set never got better. Okay, so does that make sense? And I include this plot just to point out, to illustrate that it's not as trivial as it seems to figure out when you should stop training. Because here, for example, you might think, oh, the validation error got better, but then it started getting worse. We should stop training here because we were starting to overfit, and we should use this network. But in fact, you can see that if you just keep training, we get past that local optimum and get a much better network later. So it's kind of an art, not a simple rule, to figure out when to stop training. And there's just an ocean of papers written in conferences these days about how to manage the nuances of gradient descent search and how to decide when to stop training, how to adjust your gradient to compensate for different phenomena. We're not going to go through all those because that would take a whole course, but I will touch on a couple of those in today's lecture as we're going along. Okay, but in terms of overfitting in neural networks, it's really no different from overfitting in any other kind of system we've talked about. It's just perhaps more prevalent because we have so many parameters. It makes it very easy to overfit the data. In fact, if you're trying to debug code for training a neural network, a good sanity check, a good way to debug your code is to pick a training set that has just like 2 or 3 examples and train your network. And you should see the training error just decrease, 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 and you should be able to perfectly overfit 2 or 3 examples with a complex network. And you should be happy if you see that sign, because it means your gradient descent algorithm is working properly. So it's an efficient way to sanity check your code. And then, of course, once you're sure it's working, you should use all the training data, get a better network. Okay, and so we talked before about doing k-fold cross-validation, but in the case of training networks, it's usually computationally intense. So if you have a computationally intense training algorithm or a data set, then doing leave one out cross-validation may be a little more too expensive. But here's a reasonable approach even in that cases. Use the training data to drive learning, use the validation set to decide when to, basically when to stop training. And keep in mind that even that validation set error is still a little bit optimistically biased in terms of predicting how well you'll do in the future. You know, the training error always gives you an optimistically biased estimate of how well what your test error is going to be, because you're using that training sample of training data to drive the learning, and so whatever statistical coincidences happen to occur in that data, maybe a disproportionate number of people who live in Squirrel Hill happen to have birthdays before July 1st. If you have some statistical coincidence in your data, the training algorithm should pick that up and take advantage of it to fit the data. But in the future, if you have more representative data that you're testing on, then those statistical coincidences won't be around. And for that reason, the training data is really giving you an optimistically biased estimate. But the same thing holds to a lesser degree for the validation set. Right? I might have a validation set of data that also has, because it's just a finite sample, might have some statistical coincidences that might cause the curve to dip in a particular place. And if I had a second validation set, it might not give me exactly the same curve. And so in that sense, in some sense, the validation set is getting into the training procedure. It's the thing that's telling the algorithm where to stop training. And so because it's influencing training, it also, to some degree, gives an optimistic estimate of how well we'll do in the future. So just you should keep that in mind. So if you ever publish, for example, a paper in a medical journal, don't even try to use the validation set to estimate how well you'll diagnose future patients, because the New England Journal of Medicine will just outright reject your paper for good reason. So instead, what you should do is take your data, divide it into 3 sets, a training set, a validation set, which you use this way, and then a separate test set, which no piece of the algorithm even gets to look at until the classifier is frozen. And then you test on that and report that accuracy. Okay? Okay, so I thought I would start then, since we're talking about gradient descent and problems that come up and techniques people have developed for dealing with them. I thought I would start with this. MNIST is the image data that you're going to be using for the current homework and the next homework. It's images of the digits 0 through 9. And I found this very nice paper that introduces a technique called batch normalization, which addresses one of the difficulties of using gradient descent for training complicated networks. And it so happens that they use the MNIST data set in this paper for experimenting, so I thought it would be fun to start here. They train a network, which is shown here. So they have an input image, which is 28 by 28. They use 100 hidden units, which have the usual linear function of the input. This, by the way, is not a convolutional network. It's just simply taking these pixels and running them through a 28 times 28 by 100 matrix of parameters to get these values. And they pass it through a sigmoid activation function and do that again and again. And finally, a softmax layer, which has 10 linear units output, which are the parameters for the softmax function to decide the probability distribution on the 10 possible digits. One of the problems with training deep networks that have many layers is that we get problems that people call the vanishing gradient problem or the exploding gradient problem. But you can imagine that because we're using the chain rule, remember when we derive these gradient steps, that each time, if we start at the output with our loss function and start propagating our derivatives back, if our weights are, for example, very small, then each time we apply the chain rule, we'll be multiplying probably by a number less than 1. And usually we do initialize the weights to be very small, so at least in early training, those numbers are much smaller than 1. And so if you start multiplying together a lot of weights that are smaller than 1, by the time you get back to the input, the gradients can be very small, and you end up making large changes at the output of the network, but very small changes here. The other problem can also happen where if your weights are large, then when you start multiplying together a lot of large numbers, you get humongous numbers at the input, making the gradients extremely large. And so people talk about the vanishing gradient problem and the exploding gradient problem. And as I mentioned, there are a lot of papers out there trying to figure out how to address this. But one of the most effective techniques, and it really just came up in 2015, this is the paper that introduced the technique, is called batch normalization. And it's based on the following primarily empirical observation, which is that these networks tend to train better if the activations in the network are the different activations at a given level, say these 100 outputs, if those activations are kind of on the same scale. Sometimes you have more trouble if you have X1, if the output here you have 100 outputs, and if one of them varies between 0.1 and minus 0.1, and the other varies between 99 and 9,000, then they're not on the same scale, and that tends to empirically lead to more headaches with gradient training. So the idea of batch normalization is to fix that problem, to fix it by introducing a new layer, by basically adjusting the output of each layer so that the different activities here have the same mean and the same variance. And so, in fact, here is the idea. This is used in the context of stochastic gradient descent, where we have a batch of examples. You know, the extreme version of stochastic gradient descent, we take one example and compute the derivative with respect to one example. But the less extreme version, we use a batch of examples. We might have 1 million training examples. We might use a batch of 20 to compute the gradient with respect to those 20, take a gradient step, and then get a new batch of 20. And the key idea here in batch normalization is basically to add new layers to the network whenever we have one of the linear products right before it goes into the activation function. We do the following step. For every time we have a new mini batch to calculate our gradient, what we're going to do is scale each feature at that level at that layer in the network, to scale each feature to have mean 0 over the examples in the mini batch. So if I have 20 examples in my mini batch, I look at feature 17, and I look at what value I get for feature 17 over those 20 mini batch examples. I calculate the mean of those 20 values, and I subtract it from each value of feature 17. So I just force it to have mean 0. And similarly, I force it to have variance 1. And so basically what you do is if I have m examples in my mini batch, I first calculate the mean over those m examples of feature I. I get the variance also. And then I fix x sub I for every one of those examples for feature I, every example in the mini batch. I replace the old xi by a new one, I'll call it xi hat, which is just its old value minus the mean divided by the variance. So this is, people often call this standard normalizing a variable. You take it and you fix it with this transformation so that the mean of this variable is now 0. And the variance of this is now 1 because you divided it by the standard deviation. Epsilon here is just here as kind of a numerical stability thing. So you can pretty much ignore epsilon. Okay, but now you don't stop there. You actually replace each x sub I by this, but then you actually insert a new layer into the network here called the batch normalization layer. It takes as input the old x's. It produces as output a y, which is the new x, times something plus something. And so these two parameters, the gamma and the beta here, are still are parameters that the network is now allowed to train during training. And so the way you should think of this is what the batch normalization network primarily does, suppose this is 0 and this is 1, then I'm just saying it outputs the standard normalized version of the variable. But then it introduces two more parameters that the network can train in case subsequent layers of the network don't like this to have mean 0. They can add an offset. And if they don't like the variance being 1, they can scale. So this basically makes the xi's have mean 0, variance 1, but it still gives the network the ability to train these parameters if some other mean and some other variance would be helpful. So it sounds like you're just kind of doing something and then allowing the network to undo it. But the key point here is that you initialize these to 0 and 1. So when you start training, all these things are indeed mean 0, variance 1. They're all on the same scale, and it gets rid of the problem that empirically seems to cause a lot of grief, which is variables at the same level that have different scales and different means. Okay, so that's it. And so then that leads to the following overall algorithm. Here's what we just talked about. During training, so somebody gives you a network and you say we want to do batch normalization on this network. They give you a network N. We're going to make first a training network by applying that algorithm that I just said. That is, we're going to add a batch normalization layer. Suppose you say here are k different layers in my network where I want to do batch normalization. Then for each of those you add a batch normalization layer, which is defined just like we said here. And it used to input, when it inputs x, now you output y instead. So you insert those. And then when you train the network, you allow it to update the parameters theta of the original network, plus these gamma and betas, which are the things that allow the network to rescale. Okay, so then you train it. And now when you're done, you want to make the Bayes network with frozen parameters so that you can classify new examples, do inference. And so what you do here is you just you basically compute the means and the variances over different mini batches of data to put a final adjustment so that the y that's output uses this learned beta and this learned gamma, but it adjusts for the fact that you trained on these mini batches, and therefore the variances you're getting are partly a function of the mini batch size. And so this is just a kind of a final tweak to compensate for that. But basically, the key idea is to insert those new layers, that each of which does batch normalization, and each of which introduces two new parameters, the beta for offset and the gamma for stretching, rescaling. So how does this work? Well, if we start with that network and we apply batch normalization, then what we're going to do is we're going to add a new layer here between the output of this and before the sigmoid activations. Similarly here, similarly there. In the paper, they said that they experimented with different things that you could put it in other places you could imagine. But they said this worked well. So they inserted basically 3 batch network layers. And then here's what they found. Here's a plot of the accuracy for classifying the digits between 0 and 9 as a function of the number of gradient descent steps, the number of training iterations. And the blue curve is when they introduce the batch normalization. And the dashed curve is the original network. So you can see this had a dramatic effect. Furthermore, these 2 plots, let's read the caption. Batch normalization helps the network train faster and achieve higher accuracy. The evolution, B and C, show the evolution of the input distributions. I'm pretty sure what that really means is the mean of the mini batch activations into a typical sigmoid over the course of training, shown as the 15, 50, and 85th percentiles. So, right, so if you take a mini batch of 20 examples and you have 100 features, which they had at each layer, so for any given feature, here they're showing a representative one, over the different mini batches, you're going to get different means. And so what they're showing here is what the mean activation for this particular feature they're illustrating looks like, again, as a function of training. So it's the same horizontal axis as here. And so what you can see is that the means in the mini batches jump around a lot. But with the batch normalization layers inserted, those means are much smoother. So the earlier batch normalization layers will make these outputs more smooth so that these outputs won't be as jagged. Its batch normalization will make it more smooth. And throughout, you end up with much smoother gradients. And you can see that this kind of deals with the disappearing gradient issue to some degree. It helps with the disappearing gradient issue because it assures that you have at least the same variance and scales of activity at the different layers. You can still have problems because you could have very small weights and big weights and so forth, but you get the idea. Okay, so people don't really have yet a theory that proves this is a good idea, but this is a pretty interesting set of experimental results, and so I wanted to introduce the idea to you. It's really one of the hot topics these days in deep networks. Yes? You wonder?
I don't really understand whether that how reducing gamma and
Okay, so the question is, what really is the role of introducing that beta and that gamma here? And the answer is simply that depending on what's happening in the network, it might be a disadvantage to, for example, make all of these examples have mean 0. It could be that there's valuable information that we're subtracting out here, that the mean was actually 9, and we're subtracting it out because we're trying to create a situation where the different features at the same layer have similar scale and variance. But it might, in fact, not be a great idea to go that far. And so this is kind of a hedge that allows the network to learn the value of beta and gamma that it wants, even if we want it to be 0 and 1 so that the gradient descent steps will work better. So it's kind of a hedge. Okay. Okay, so as I said, it's really, there are issues with gradient descent. Batch normalization is a popular idea right now for trying to deal with it. There are ideas also about how to adapt the learning rate over time. Usually you start with a higher learning rate, and as you get closer and closer to finishing, you reduce the learning rate. That helps you not jump over the minima or the optima that you find. There are also ideas for how to initialize weights. For example, Jeff Hinton says you should initialize weights based on how many inputs there are to the unit. And if you have 3 inputs to one unit, but 30 inputs to a different unit, then you should use smaller weights for the 30 input unit. And that, in fact, the magnitude of your random initial weights should go as the square root of n, where n is the number of inputs to the unit. So there are a lot of heuristics and analyses to try to help us engineer better gradient descent algorithms. But at this point, it's very much an engineering art rather than a provable science. So if anybody here wakes up in the morning and as you're taking your shower, it strikes you that you know how to prove that you could make gradient descent work with a particular rule, write it down. Come see me and I'll give you a guest lecture in the class. But it's an open problem. Okay, so to move on, there is some theory, on the other hand, about what are the functions that neural networks can express. It's a reasonable question to ask. When we started with decision trees, one of the first questions we asked was, what are the functions decision trees can represent? And you told me that, correctly, that if we have discrete valued y's, decision trees can represent any function over the x's. Well, so here's some interesting facts. If we have a Boolean function, by which I mean Boolean inputs, Boolean outputs, then every Boolean function can be represented by a network with a single hidden layer. If you're an electrical engineer, you probably already know this from your circuit design class, because it's also widely known that you can design circuits that are only 2 gates deep if you want to implement any Boolean function. However, you might need an exponential number of width of hidden units in that 2-layer network. When I say exponential, I mean exponential in the number of inputs to the network. But that's a fact. When you get to continuous functions, it's actually surprising to me. Every bounded continuous function can be approximated with arbitrarily small error by a network with just one hidden layer. Again, no guarantees on how wide that hidden layer will have to be. And furthermore, any function, even if it's not a bounded continuous function, can be approximated to arbitrary accuracy with 2 hidden layers. So these are kind of interesting statements because they tell us something about the expressive power of neural networks, for example, made of sigmoid units. But they're also interesting because today's neural networks often have many dozens of layers. So it's not unusual to see a network with 50 layers. And so there's something going on in today's networks that is not explained by this theoretical set of theoretical results. And in fact, there's a very interesting paper I can point you to by Russ Solek-Kutenoff, one of the professors here in the machine learning department, from earlier this year, looking at the question of why deeper networks sometimes generalize better than shallower networks, even though they have more parameters. And so trying to study that phenomenon. So these theoretical results hold, but it's I think, helpful to keep in mind that as a practical matter, people are finding it very useful to train networks with dozens of layers despite this. We don't really understand why. Okay, so I want to move on to a different topic, which is, as I mentioned several times in the last couple of lectures, I think one of the most important properties of deep nets is that they learn representations. And I think I mentioned that there's now a conference called the ICLR, International Conference on Learning Representations, which is mostly a deep networks conference. But here's a very simple network that tests your ability to think about this. So suppose I want to train a network. It has 8 inputs, 3 hidden units, and then 8 outputs. Okay, I'm just going to goes this direction. And here are the 8 training examples that I'm going to use to train it. Notice each of these is what people call a one-hot vector. That is, it's all zeros with a single one. And then the output of the network is actually exactly the same as the input. So I'm training this network to be the identity function. People call these kind of networks autoencoders. Because it outputs the same thing you give it as input. So let me just ask you, do you think that this network can actually represent that function, given that it only has 3 hidden units? So somehow that hidden layer is going to have to represent the input in a way that distinguishes all 8 of the possible examples I'm training on. Okay, how many say yes? How many say no? Okay, so I tried this. I trained it. And the answer is yes, it works. And here what I've done is, when I show the input and I round up the output to the closest to a 1 or a 0. If the output is 0.04, I round that down to a 0. If the output is 0.9, I round it up to a 1. So after training, it successfully takes these inputs and outputs these results. And here are the hidden values of those 3 nodes that it comes up with after it's successfully trained to do this. So if it sees this input, the 3 activations in the hidden layer are there. Okay, so what I find interesting about this, do you see the pattern? It's really the Boolean code. It's the binary code for the digits 1 through 8, right? So if I round these up, here's a 1 and a 0 and a 0, a 0, 0 and a 1, a 0, 1, 0, 1, 1, 1. You get it. All the possible Boolean codes, all the possible 3-bit codes, all 8 of them, it's using. It learned to come up with this 3-bit Boolean code to represent which of the 8 inputs was provided. So I like this example because it makes you realize that it's not like we asked it to come up with a Boolean code. What we asked it to do was to minimize the sum of squared errors in these outputs given these inputs. But the only way that the network could actually succeed in that was to come up with some code in terms of 3 hidden activations that would successfully re-represent the input in 3 numbers so that it could successfully auto-encode that, successfully output what the input was. So this, yes?
So what if we had, instead of 8, we had 9?
Right, good question. The question is, what if I had 9 and I still only have 3 inputs? Then what do you think would happen? Who thinks it would work? Many fewer hands. Who thinks it won't work? Okay. Probably if you think it won't work, you're thinking with 3 bits you can only distinguish 8 numbers. That's a true statement, but that's not a good argument. The reason it's not a good argument is these aren't really Boolean values. These are real valued. So all you need to do is come up with 3 real valued, a code that uses 3 real valued numbers, not bits. And of course, even if I had just 1 real value, what if I had 1 hidden unit? Then, of course, I can code 8 different values in 1 real value easily, right? 0 to 0.1 will be the code for the first thing, 0.1 to 0.2, 0.2 to 0.3. In fact, I can code an infinite number of distinctions with a single real number. Now, the other part of the question is, with this simple single layer to get there, is it actually possible to compute that code? And I don't know the answer to that, so we'd have to run the experiment to give it 9 and see whether it could succeed. But you see, once you start getting vectors of real values, you can come up with codes that distinguish a lot of different things. Okay. All right, now, just for fun, I also made a plot while I was training this network of how the weights and the error terms changed over time. So here, for example, is that I was training this to minimize the sum of squared errors at the output. And here there are 8 outputs. And here, as a function of training, was in fact the sum of squared errors over the training set for each of those 8 outputs. And so what you can see is just kind of something about the behavior of gradient descent training. This output got lucky. It somehow, very early on in training, it got correctly implemented. So that after just 1,000 iterations, it already had a pretty good output, but this other output didn't. It had somehow, later on, once the others fell into place, then it did. And this is very typical. So what you see if you look at, say, different terms in your loss function, you'll see sometimes that's basically what I'm showing here. My loss function is sum of squared errors. And of course, in the loss function, we sum over all of the network outputs. And so here we're looking at the 8 different terms there. You often see that they don't all descend in orchestrated fashion. Sometimes you get this instead. We could also plot the evolution over iterations of weights in the network. So for example, I could pick one of those hidden units and plot, instead of the loss function, I could plot the weight values going into that hidden unit. Or I could plot, here would be a cool thing, I could plot the 3 activations in the hidden unit for a particular training example. and how that 3-bit code evolves over time. If I do that, here's what I get. So here's showing the 3 hidden unit values, for example, after 500 training iterations. When I input this training example, here are the 3 values of the hidden unit activations. But you can see that actually wanders around, finally converges to where the network decides to assign that particular thing 110 encoding, basically, to speak in Boolean terms. But you can see that during the gradient descent tuning and learning of the network, that encoding was actually moving around before it converged. I think this is a really good way. These kind of plots are a really nice way to try to understand what's going on as you train your network. So, in fact, in the next homework assignment, you'll have some code. You're welcome to produce these kind of plots just for fun so that you can actually see what's going on as you train the network. Okay. And here are, in fact, the weights to a single hidden unit. Of course, there are 8, I guess there are 9 incoming weights to the unit because there's also the bias, the B term, in addition to the weights from each of the 8 inputs. But again, you can see how those weights coming into a particular hidden unit, I started them out with small random values close to 0, but then with training, they moved around. I find it interesting that this particular weight ended up being 0 in the end. What that means is that there's 1 bit out of the 8 inputs that this hidden unit is just totally ignoring. Okay. All right, so I encourage you to, especially in the upcoming homework assignment, to, please yourself, but take a look as you're training the network at how these things are evolving. It's really a good way to get some grounded feeling for how these gradient descent methods work. Okay, so here's another example of a network. For image classification. This one, I might have mentioned this earlier in class, but in a prehistoric version of this machine learning class, we actually took photographs of all of the students, all 26 of them, I think it was. Here are some of the training examples, the pictures we took. And then we trained a network that had 30 by 32 pixel inputs, 3 hidden units, and then 4 output units. This was a 2-layer sigmoid network. And the goal of the network was to output a 1-hot encoding, a softmax encoding, to indicate whether the person was looking left, straight, right, or up. And the network learns this with 90% accuracy. You can grab the data and try it yourself if you like. But I bring this up so that we can look at the learned internal representations for this. So we can look at the 3 hidden units that were learned, just as we looked at the autoencoder, once the network was trained to distinguish these different 4 possible head poses. And here's what we get if you do that. So in this case, what I've plotted here are the input weights from the input to the hidden layer. Okay? And so, of course, there's a weight for each pixel in the image. And I've displayed these weights so that white means a high positive weight, Black means a large negative weight. Gray means close to 0. And so once it's trained to correctly classify head pose, at least with 90% accuracy, here are the learned weights displayed on the same grid as the input image. And so if you look at those, you can see there's some kind of ghostly face-like image there. But it's hard to say exactly what's going on in those layers. And similarly, this is, these are the weights from the hidden layer. Oops. From the hidden units to the output that is for straight ahead. And even though there are 3 hidden units, of course, there are 4 weights because one of them is for that bias term, the B term. I call it W0 in this plot. Okay, so there's the kind of thing you see. If you actually look at this, like let's look at that middle weight, set of weights. So the middle hidden unit. If I give it this image, I think I'll get a large positive value, right? Because you can see it has, sort of in this part of the image, it has large positive weights. If I multiply those by large positive pixels, this is grayscale, then I'm going to get a large positive output from that set of weights times these pixels. And so I think that unit will have a big magnitude for this, but not for this one, because here in that same region, it's going to be much darker. And so it's interesting because then if you look at that second unit, this is the weight from that second unit to the network output that's indicating the person's looking to their right. So there's a kind of possible interpretation of what's going on here, right? It has learned that if there's light pixels in this part of the region, then there's a good chance that the person's looking to their right, and that's captured by the output unit that goes in. So this is one of the good cases where you can kind of get a glimpse of how the network is performing the classification. You can kind of jive it with your own intuition. But in many cases, especially if you have 1 million parameters in your network and dozens of layers, it gets to be much more difficult to examine. Even this is pretty difficult. So one of the common complaints about deep networks is that they can't explain why they're doing what they're doing. They might be able to recognize your mother in a photograph, but they can't explain how they recognize your mother in a photograph. And so maybe that's okay for finding your mother in a photograph, but if it's a medical diagnosis problem, you'd kind of like them to be able to explain. The counter to that, of course, is that you also can't explain how you recognize your mother. Even though you know how to do it, you really can't write down an algorithm to do it. So, in fact, people tried that, tried writing manually face recognition programs for many years, and then it just didn't work. But today, it's easy to train a program to recognize your mother. You just give it photographs and say, here's my mother, this one's not, this one is. And it figures it out. It can't explain it either, but it can do it. So we know more than we can say. And there are a lot of skills you have that you can't explain. You can't write down the recipe. You can't even write down, you actually can't even write down on a piece of paper in words how to recognize your mother and give it to the person on your left and expect them to go through photographs and do it accurately. So it's kind of like recognize your mother, tie your shoes, all kinds of things you know how to do. It's tough to explain. Anyway, deep networks are no better off than we are in that, but maybe they're a little worse off. Okay, here's another example of a network to push further on learning representations. This is kind of the theme for today. This one comes from Jay McClelland and Tim Rogers. They trained a network to basically code relational triples. So notice the two inputs for this network are a relation like is-a or can or has, and an item like pine, oak, rose, canary, salmon. And the outputs are values of the relation. So for example, when they train this, they train it to say a canary, they make that a one-hot vector, all zeros and a single one. Canary can sing, fly, move, and grow. That's what canaries can do. They can't bark, and so forth. And so I find this network interesting too because it gets at how networks might actually encode relational triples. And so you see what they basically did is they have a relation that relates an item to an attribute, and they train it so that you give the relation and the item as input, and then it outputs the attribute. And you see how they set this up. It's kind of interesting. So they trained a network with this structure. You see what this network, what this layer in the network is doing is converting the one-hot encoding, all zeros with a single one, to a distributed representation. It's like going from the one-hot 7 zeros and a 1 through our 3-bit internal code back out. And so the 3-bit code ended up learning the Boolean code for digits 1 through 8. Here it has to learn some other kind of code that will be helpful when passing through another layer to finally output what those properties are. So this hidden representation is actually learning something about what are the commonalities among these different items and how do they enable different relations. So it's interesting to just think about how you would design. But I think this is a pretty interesting design at the time. Okay, so just as another example from thinking about internal representations. More recently, there's a lot of work in the area of natural language processing for using deep networks. And it has kind of revolutionized, well, not kind of, it has revolutionized the field of natural language processing over a very brief period of time, less than 10 years. And a lot of it is because deep networks give us a way of learning distributed representations for words. And in the past, people would try to write programs, for example, to parse sentences or to find the nouns and the verbs, the parts of speech, or to predict the probability distribution of the next word, to predict the next word in a sequence. If I say, parked my car in the, you have your idea about what the next word might be. And so these are kinds of tasks that people have worked on for a long time. And deep networks seem, for all of those tasks, to perform much better. And the reason, effectively, is because the earlier approaches to those tasks treated words as atomic symbols. If I had a word like parked, P-A-R-K-E-D, that was just a symbol. And I might have 50,000 words that are a set of symbols. But it's just a set of symbols. There's no relation among those symbols. But now, deep networks give us a way to learn vector representations for each word. And people call those vector embeddings for words. That's the terminology people tend to use. But now it's as though every symbol has a vector associated with it. And the significance of that is that now it's not just a set of symbols. Every symbol lives in some Euclidean space, in the Euclidean space of that vector embedding. And so now we can talk about how similar, how distant the symbol cat is from the symbol meow or the symbol airplane. And the vector embeddings that end up getting learned basically define now a distance metric over these symbols. So instead of having just a set of atomic symbols with no relations among them, once we attach a vector code to each symbol, then for free we get this Euclidean distance metric. And that turns out to, in fact, be remarkably valuable, useful. So let's look at one of the most popular these days is called word2vec. In fact, this is a set of 300-dimensional vectors, one for each word in English, more or less, that you can download from the web if you want to get a vector, 300-dimensional vector for each word, and then use it for something. But let's see how it was learned and how it was set up. So it's based on what we call the skipgram model, which is a very simple idea. Given a sequence of words, like news articles, for example, we'd see sequences of words maybe like the dog jumped over the fence in order to get to whatever. We train a network that on every word, and the job of the network is to predict the words before and after it. Okay, so we would train a network when the input to the network was here, then the output of the network should predict what this word is, what this word is, what this word is, what that word is. And then the same network, when we put it over this word, should predict the two to its right and left. Okay, so that's how we're going to get training examples. We'll just get gazillions of words of text and train a network to do this. And then it's the hidden layer that's going to, just like in the canary example, we start out with a one-hot encoding. This word initially is just 50,000 zeros and a single one to indicate that it's the word fence. But now it's going to go into a hidden layer, just like the one-hot encoding here had to then go into a learned vector representation to be used for something. In the case of the skipgram model, the word is being used to predict what are the words near it. Okay, so, and if we start looking at a lot of text, then we might start seeing things like, oh, dog and cat have some similarities. Sometimes they're surrounded by similar words. Dog maybe is more similar to cat in terms of the words around it than dog is to, say, window. And that's the regularity that we're counting on the network to learn. Okay, so here's the skipgram model. Basically, as I said, we input one word. It has to go to some distributed representation from which we predict the vector code for each of the other words. And so this is trained so that we sum over T is our sequence indicator. So over a sequence of words, we want to maximize our predicted probability for the word that's going to occur at position T plus J, given the word that's at position T. And then J can range from -2 to -1 to +1 to +2, or in general from -C to +C. And we'll use the softmax style output, where the probability of the output word given the input word in the network is just the softmax expression, where here we're summing over all the possible words. So this might be a sum over 50,000 words. It's a little bit of a efficiency hit. But that's it. It's a simple, basically simple two-layer network. There are some efficiency issues. So if you look at this paper by Mikolov et al., which introduced this only 4 years ago, they talk about some, they present this as the basic model, but then, for example, there's an issue here because if there are 50,000 possible words in your vocabulary, this is a big sum and it's very expensive to calculate all that. And so they use something they call hierarchical softmax, where instead of the softmax being defined this way, there's basically a tree. The thing we usually do in computer science when we want to deal with large things, we build a hierarchy, a tree, so that we have to go down the branches of the tree to get to the thing we're looking for, and we can therefore save computation as we go down the tree. So that's it. So they introduced a couple optimizations like hierarchical softmax, negative sampling. They don't want to train just on positive examples. So they will also introduce words that don't occur next to a word and present it as a negative example. And they also, for the most common words like the, they reduce the frequency of those. So they had some optimizations. But the key idea is this simple. And then so what you do is you end up learning a hidden representation just like we did for the 838 network that was the autoencoder. And then you can use that representation of the word. How? Well, here's what they found the properties of this had. If they trained a 100-dimensional hidden layer for the words using that network, and then if they projected that down to 2 dimensions, using, in this case, principal components analysis, which we'll talk about later on in the course, if you don't already know it. But then what they found was that there's this kind of interesting relationship. If you take that 100-dimensional vector and squeeze it, plot them on a 2-dimensional space, then they find the relationship between Portugal and Lisbon is kind of in the same direction in the vector space as the relationship between France and Paris and Poland and Warsaw. So there's some interesting semantics that's coming out of these learned vector representations, that it's almost like there's a vector algebra that you could start at any of these countries and add in a vector in this direction, and it should put you close to the, in this case, capital of that country. So they explored this further, and so as the table caption says, they trained on 783 million words of text. They built a 300-dimensional word embedding vector for each word. And then they looked, they set up basically a set of analogy problems like this, where they say, word 1 is to word 2 as word 3 is to what, and the program has to answer it. And the algorithm is simply, if I say, for example, France is to Paris as Italy is to what they'll do is they'll say, let's take the vector for Paris, subtract the country France, and then add the country Italy. And when they do, the top word that comes out is Rome. And France is to Paris, as Japan is to Tokyo, as Florida is to Tallahassee. Or Japan is to sushi. This one isn't quite as good as Germany is to bratwurst. I think that's right. France is not really tapas. Spain would be tapas, but And US to pizza, I guess that's probably pretty good. But you see what's happening here is they're doing vector arithmetic on these word embedding vectors to solve analogy problems. So this is one of the properties that comes out of taking these things that used to be just symbols, unrelated, and training a network to assign a vector code based on what's the probability distribution of words that tend to surround this word in normal text. And then they're finding that they can basically do this kind of algebra on the vectors. Remarkable. Here's an experiment we did in a paper that we published this summer that also learns vector embeddings for noun phrases and entities in a knowledge base, but also tries to explicitly learn relations as well. So we have a system, I'll talk more about this probably later on in the semester, but we have a system we call our never-ending language learner, which has been learning to read the web, and it has a collection of knowledge triples that it has built up over time, including these. Like it believes the Maple Leafs is a noun phrase that refers to a team that won something called the Stanley Cup. And so did the Red Wings, whose hometown is Detroit, which has a company called GM, which competes with Toyota, etc. So Nell has built up a knowledge base with over 100 million of these kind of triples in it at different levels of confidence. Here I'm displaying just high confidence ones. But we decided we should try to learn vector embeddings for every node in this 100 million node graph. And furthermore, we should try to learn embeddings for every relation. If we have a relation like city has a paper, or paper has a writer, or team has a stadium, we should try to learn relations embeddings too. So we set it up this way. We said, let's take the triples that are in that graph, like coffee is a beverage, Pittsburgh home to team Steelers. And each entity will assign a vector embedding, let's call it V sub E. And each relation will assign a matrix embedding. And we'll train it so that the assigned vectors and the assigned matrices assign a score to every possible triple. So if I want to know if relation R holds between entity 1 and entity 2, what I'll do is I'll take the vector embedding for entity 2, I'll multiply it by a matrix, which represents relation R. If you multiply a vector times a matrix, you'll get another vector. Then I'll take the result of that and multiply it by entity 1 vector. So this vector times the matrix give me a vector. I multiply it by that vector. It's a dot product. I get a scalar, a value out. So we thought, we'll just train this so that the value of that scalar, once we multiply this, is high if the relation is true, that is, if Nell believes it, and low otherwise. So we trained it on 180,000 entities that are in Nell's knowledge base. These belong to a lot of different semantic categories, like pen is a utensil, I think, and coffee is a beverage, and love is an emotion. So Nell has a lot of semantic categories. And we trained it to minimize this. Here was the loss function. So what we did was we say, well, we'll sum over our training example of true triples, like Pittsburgh home to team Steelers, whatever's in the knowledge base, we'll assume it's true. Plus we'll sum over other triples which have the same entity and relationship, but we switch out the other entity. And we don't know what's false, so we just randomly chose another entity. So if it says Pittsburgh is home to Team Steelers, then we'll make up a negative example. Pittsburgh is home to Team, and we'll just randomly pick an entity, like Penn. Pittsburgh is home to Team Penn. But then we sum over those triples. This quantity, which is, this product is the score for this relation. And so what we're doing is we're saying we want to learn these embeddings so that we minimize, this is the distance between the score for a relation we believe is true versus one that we believe is false. And so we want the true one to be bigger than the small one by at least 1. And if it is, then that's fine. And we'll just use 0. But if it's not, if these are flipped or if even if they're close, then we'll pay a penalty. So this is a way of training a system. We put the max in there. You see the intuition behind the max was just that we didn't want the system to put too much energy into further separating things that were already pretty far apart. Okay? So when we did that, what we found was when we went to the relation is-a, like Pittsburgh is a city, or anxiety is an emotion, then we found that the system was 88% accurate, classifying arbitrary noun phrase entities into the correct 1 out of 258 categories. So, the chance level of performance here is less than 1%. But with these learned embeddings, we're getting 88%. So there's a lot of information being captured here. And so if you look at what those look like, here it is. We project those learned embeddings down to a 2-dimensional space. Here are the learned embeddings for the 258 categories themselves. The categories get a vector as well as the ground entities. And so, for example, if you blow up this portion, you see this is the category bedroom item, like bed, cabinet. This is the category floor item, furniture, household item, hallway item, building feature, table item. So these 8 or 9 categories end up having vector embeddings which are very similar to one another. Whereas over here in green is another set of categories which are cell type, lymph node, artery, vein, body part, brain tissue, bone. Those are other categories that Nell works with, but their vector embedding is very far away. They're very dissimilar to these. So that's the kind of structure that you get. I could blow that up a little bit more to make it more visible. Now you can see all like the bedroom item, floor item. What are the other categories in the neighborhood here? Well, here's politician, politician US, male, astronaut, monarch. These are all categories in Nell. CEO, US person, professor. So these are like people type categories. Comedian, director. Then we get into things like winery, planet, cafe, restaurant, machine learning data set, continent, chef. So like here are the people, and the people bleed into, well, the most extreme person here is the chef. But that's near winery and restaurant. So you start to see the kind of semantics that come out of this. Here is a plot of not just the categories. The categories are now in brown. But the blue dots are just noun phrases that became entities in Nell. And so, again, if we look at those, there are 3 categories that are very nearby each other: bedroom item, bathroom item, and kitchen item. But now if you look, here's like a flowered board. It's very close to kitchen item. Or a skillet, small skillet, heavy, large skillet, water container, plastic sheets, coffee set, tea kettle, shot glass, oil pan. Over here by bathroom we have seat cover, vanity unit, jacuzzi, glass enclosed showers, towel bars, sinks, electric shower. And then up there we get things closer to bedroom item, which are things like tables, makeup mirror, bedstand, and so forth. And right here in the middle, like halfway between bedroom item and bathroom item, is brush, which kind of seems right. You might find the brush is kind of related to both of those things. So this is the kind of semantic embedding that we get. And again, at least for the relation ISA, these vectors learned jointly with the relation is able to provide 88% accuracy classifying new items. So I think I will end there for today. And we'll pick this up again next time. Next time we're going to talk about sequential models. Like word processing really is a sequence of words, or predicting the stock market is really a sequence of time. So we'll look at networks for those next time.